Now let's consider the idea of a well-formed formula. Intuitively, a well-formed formula is an expression that we can write down that follows the rules and expectations of the elements. So what does that mean? Well, let's review our elements. So we have propositions, we have operators. The operators are these five, not P, P and Q, P or Q, P implies Q, and P is equivalent to Q, and groupers. And groupers, again, tell us the scope that an operator has. All right, so now, here is a little bit more formal definition of a well-formed formula. A well-formed formula is a proposition, or what results from joining propositions together using operators correctly and indicating the scope of the operators with groupers. So let's sort of build up this idea. So let's consider H again. I have a headache. That's a well-formed formula because it's just a proposition. It's an assertion about the world. But if we take this proposition, we take another proposition, and we join the two propositions together using the correct form of, say, the operator conjunction, then we get a proposition, and it's a well-formed formula because we've, in a sense, followed the rules for constructing an expression with conjunction. Let's take another example. If I take the proposition H, I have headache, and I rewrite, I write a proposition, it's not the case that I have a headache. This is a well-formed formula because we started with a proposition and we used negation correctly applied to that proposition. So now we need to explore what does it mean to use an operator correctly. This is where the geometric shapes come into play. If this represents a proposition, then the correct use of negation is when you have its scope, which is going to be in the box, and it's a proposition, and the negation applies to whatever is in the box. So notice this form is you have negation operating on whatever is in the box that's immediately to its right. It could be a simple atomic proposition. I mean, like the variable p is atomic because it doesn't have anything, it has no other structure, or it can be molecular like P and Q. The point is, everything in this box is the scope of the not operator, and so as long as it's clear that the not is applying to a proposition that goes in its box, then it's being used correctly. So this is a well-formed formula. Why is it a well-formed formula? Because P is a well-formed formula because it's a propositional variable. And not P is a well-formed formula because not is being used correctly, which means not applies to whatever is in the slot or the box on its right. This is also a well-formed formula. Suppose we have the expression P and Q, and we put that in parentheses to indicate that it goes together, and we put a not on the outside of that. Why is that a well-formed formula? Because, again, not is being applied to everything in the box that it operates on, and what goes in the box, all it has to be is a proposition that's a well-formed formula, and sure enough, this is a well-formed formula. Now let's investigate why this is a well-formed formula. See, if we break it down, we will see that the AND operator operates on a square on one side that contains a proposition and a triangle on the other side that contains a proposition. So as long as it's clear that what this AND operator is operating on is a proposition on the left-hand side and another proposition on the right-hand side, then this whole is a well-formed formula. So I hope you're beginning to see the idea here. So a well-formed formula is either a proposition, and that's a constant or a variable like P, or what results from the proper use of an operator, like not P or P and Q, because that follows this schema, or P implies Q. Notice it's the same basic idea. You've got a proposition on the left-hand side and a proposition on the right-hand side. And so as long as you're following the same basic schema of the operator, and this, let's think of this as an abstract schema, which we can write with variables, but this can be helpful because it really illustrates more graphically what's going on here. So the schema of the AND operator is a box that contains a proposition on one side, and as I've said before, a triangle on the other side that contains a proposition. So now let's look at some expressions and see if we can identify which expressions are well-formed formulas. What about the expression P implies Q? Well, it follows the schema for implication just right. How do we know that? We can analyze it. So here's a proposition on the left-hand side, a proposition on the right-hand side. So that is a well-formed formula. But consider this. It's not the case that P implies Q. Is this a well-formed formula? Well, let's analyze it. To start with, we can see that the negation operator is used correctly because it applies to a box on its right-hand side. And what's in that box, let's just pull this out of the box and we'll look at it more closely. What's inside the box is this expression. We know that it all belongs together in the box because of the groupers. The groupers say treat this as a single unit with respect to an operator that's operating on it. When it's by itself, of course, we wouldn't need the groupers because it'd be clear that the expression goes together, P and Q. So if we remove the groupers, we see just the expression P implies Q. And now we can analyze this into the logical form, this for material implication, and we can see that on this side, the variable P is being operated on by the implication, and on this side, the variable Q is being operated on. Now notice, when we get to this level, we just have an atomic propositional variable with no operators or anything going on, and so we can see how in this chain we build up. Since P is a proposition, that's a well-formed formula, and Q is a proposition, it's a well-formed formula, then P implies Q is a well-formed formula, again, because we're using material implication correctly. And if P implies Q is grouped together as a well-formed formula, then it's not the case that P implies Q is a well-formed formula, because this well-formed formula takes this well-formed formula and applies negation to it properly or correctly or according to the syntax of the negation sign. So you might be thinking, okay, well-formed formula, but as opposed to what? Well, look at this expression. This expression cannot be analyzed into a proposition and the correct use of operators, because we've got kind of a mess here. Like if, let's say we go from the outside here and we look at the negation operator, what the operator appears to be operating on is this expression. But the problem is this is not a well-formed formula because it's not a correct application of this disjunction. What does disjunction have to look like? It has to have a proposition on the left-hand side joined together to a proposition on the right-hand side. So notice what we're missing in this expression is we're missing the whole left-hand side. So because we're missing that whole left-hand side, this is not a well-formed formula. It's missing a piece. And so this expression can't be a well-formed formula. In fact, this expression is just nonsense. It's a misuse of our symbols or the syntax of our symbols, right? It'd be kind of like if we just strung together a bunch of mathematical symbols in a way that just made no sense at all, like the square root sign with a plus under it. I mean, see, this is not a well-formed formula because it's just nonsense. It's the same kind of idea. The more formal way to talk about it is that we have to obey the syntax of each of our operators. So now, if you think about this, let's go back to that page where here's our operator list again. So if you look at this list of operators, what you'll see, there we go. Okay, what you'll see in these operators is 4 of these operators have a similar structure in that there's an operator that joins something on the left with something on the right. So the syntax of all of these is more or less analogous. The operator is different. We'll learn what those operators mean, but the syntax is pretty similar. Each one of these can be analyzed into an operator that joins 2 things together, one on the left-hand side, one on the right-hand side. And we have one operator that has only one slot, the negation operator. It has only one slot, and that slot is always on the right-hand side. So what we say about this is that the negation operator is a unary operator, meaning it has only one slot, and these other 4 are binary, which means they have 2 slots, one on the right and one on the left. So the syntax for these expressions depends on whether it's unary or binary. If it's a unary operator, then negation, it has to have the slot, as we see here, on the right-hand side in that slot, that argument space, that has to contain a proposition, which, of course, is going to be a well-formed formula. If it's a binary operator, then it behaves like this, in which case the 2 sides, the left side and the right side, have to be occupied by well-formed formulas. And then, just to remind you, we use groupers to indicate what is contained within the slots, these geometric shapes, of the operators. A more formal way to say that is groupers identify the scope of the operator so that we can understand the syntax.